Okay, so 2.5 zeros of polynomials, we're basically going to talk about three things, a lot of which we've already even talked about in class. So we'll have our rational zero theorem, which is just going to give us all of the possible rational zeros. Then we'll talk about properties of polynomials that have to do with their degrees and their factors. And then finally, the linear factorization theorem. So starting with our rational zero theorem, basically what this says, if we have some polynomial, it's going to have a leading coefficient and a constant term. So first term and last term. You're always going to have all of your possible rational roots, and again, that means rational roots, not all real roots, doesn't mean irrationals and doesn't mean complex. So it's integers and fractions. And anytime we have that, your zeros, if they exist, will be the factors of p over the factors of q. And what that looks like is if I have an example here, you see my q is 2 and my p is also 2, which means factors of 2 would be plus or minus 1 and plus or minus 2. And factors of q in this case happen to be the same thing. So if I have a rational zero, it would be of the form p over q. Meaning, I can take all these, I can take these p's, put them over the first q, 1. I end up with the same thing. Plus or minus 1 over 1, plus or minus 2 over 1, and that gets plus or minus 1, plus or minus 2. Then I take these and put them over the second term. So plus or minus 1 over 2, and then plus or minus 2 over 2 is just going to give us 1 again. So this would be all the rational zeros. If 1 exists, it is one of these 6 numbers. Plus or minus 1, plus or minus 2, plus or minus 1/2. Properties of polynomials then. If we have degree n, then we know there are going to be n zeros. And again, remember that could be complex or real. If one of them is complex, they always exist in conjugate pairs. So if there's one complex, there has to be a second complex, and it's the conjugate. And if we have degree n, that means there are going to be n factors, okay? One corresponding to each of the zeros, whether it's real or complex. Okay, so what that means, if we want to find all of the zeros of this one, going back to our p over q, we have p is negative 2, so that means we have plus or minus 1, plus or minus 2. And then q, the tricky part here, is 15. So we have plus or minus 1, 3, 5, and 15. Putting p over q, we're going to have plus or minus 1, plus or minus 2, and then a bunch of others because we have to put each of these over all those. So plus or minus 1/3, plus or minus 2/3, plus or minus 1/5, plus or minus 2/5, and then plus or minus 1/15, and plus or minus 2 over 15. Okay, so one of these, if there's a zero, exists. Also remember, since we have a degree 3, that tells us there's 3 zeros. And so what we're going to do here then is use our remainder theorem to find that first zero. And that means if we take each of those zeros, or one of them, and plug it in, I'm going to start with f of 1. If I plug that in, what number do I get out? Now if it's a 0, you should get out a 0 here. So to plug that in, I'm going to say 15 times 1 to the 3rd, let's see, plus 14 times 1 squared, minus 3 times 1 minus 2. And that gives me, that gives me positive 24. So we know that 1 is not a 0. So just going down the line, I'm going to say f of negative 1 then. So I'm going to say 15 and then negative 1 to the 3rd, plus 14 times negative 1 squared, minus 3 times negative 1, minus 2, and I get 0 for that. And now this is what we want to do. So this tells us that negative 1 is 0, which also tells us that x plus 1 is a factor. Okay, that's what your linear factorization theorem says, or factor theorem says. That if we have a 0, the opposite, x plus 1, is going to be a factor. So now we're going to do synthetic division. So I put negative 1 here, and I'm going to go back and use my coefficients, 15, 14, negative 3, and negative 2. So 15, 14, negative 3, and negative 2. Okay, double check those again. 15, x cubed, x squared, x, and a constant. So remember synthetic division from last section. I just bring down my 15, multiply by negative 1, so I get a negative 1. Multiply again by negative 1, so I get 1, which gives me negative 2. Multiply by negative 1, I get positive 2, and so 0. So my other factor then would be 15x squared minus x minus 2. So I know 1, 0 is negative 1 because of this. Then I need to find the factors of this. So if I use my quadratic formula and I plug in 15 for A, negative 1 for B, and negative 2 for C, I'm going to get my other two zeros from this, which would be x equals a negative 1/3 and x equals 0.4, or that would also be the same as 2/5, which you'll notice both of these are up here. There's your negative 1/3, there's your 2/5, and then we also had a negative 1. So all of our zeros were in that list. And that gives us each zero if that's what we were looking for. Okay, we could also then go a step further and graph this if we wanted. Remember to plug 0 in for x to get your y-intercept. Plot all your x-intercepts. Think about the number of turns we have. Okay, so what you're going to do for class next session is graph this function. So that's the first piece. You're going to graph this function or this polynomial. And then, the next thing you're going to do is also find this polynomial. So remember, n equals 3 is your degree. That's going to tell you how many factors. So you've got 2 of them right here because those are zeros. You can find the third using this information. Think about conjugate pairs. And then you're going to have to find A using this last piece. And that's what we're going to start class with tomorrow. So I'm going to collect those two things. And that is basically it for finding the zeros of polynomials. That's just going to help us graph a little bit. Remember, rational zero theorem has to do with P over Q. Properties of polynomials, the degree is 3 or degree is n, then you're going to have n factors, n zeros, and complex roots always come in conjugate pairs. All right, we'll see you next session.